Perfect.
That's enough of a warning.
Yes, we're very happy to have Georg Frenck from University of Augsburg talking about characteristic classes of manifold bundles over spheres. Georg,
yeah, so thanks for this introduction and the invitation to speak here. And well, let me start by fixing for today that M, whenever I will use the letter M, this will be a closed oriented manifold. And if I don't say anything, the dimension will be denoted by D. So whenever these two letters appear, you know what to do with them. Okay, so today I will talk about fiber bundles over the base space B with fiber M. So what does that mean? Just as a quick reminder, a fiber bundle is a map pi from E to B, such that locally E looks like the product of the fiber M with the base space B. And yeah, so I want to have this local identification. Okay. So before I go on, let's maybe mention a few examples so that we have something to take along for today. So, I mean, the first class of examples are products. It's because, well, everything that is actually a product will also be a local product. The second, which is also hopefully or maybe a little familiar, is the example of vector bundles. So here, my fiber is Rn. So this doesn't fall into this category of closed manifolds. But yeah, if you relax this, you can still ask for this product property if M is not closed or not oriented even. So this is here. No, this is this case. Now, third example to take along are coverings. So in this case, I have a discrete fiber. And the final one, which is a little more elaborate and which is like a sample of a bigger class, are mapping tori. So what's a mapping torus? So yeah, this works good. So mapping torus is, well, what you would expect. If your manifold M is a circle, it's actually a torus, but you don't take like an honest torus, but you take, well, your manifold, the cylinder of your manifold, and then you identify the ends of the cylinder along some diffeomorphism. So you get like a twisted torus. And well, one example to visualize this maybe is if you take M to be a circle and your identifying map to be -1, then what you get is the Klein bottle. So this is something to have in mind or have it to visualize when I'm talking about fiber bundles. And now, the main theorem that classifies these objects, these fiber bundles, is that the set of these fiber bundles up to the notion of isomorphism of bundles, which I will not write out what this means, but it's like the natural thing you could do or could define. This set of isomorphism classes is in one-to-one correspondence to homotopy classes of maps from the base space to B diff of M. Okay, so what are all these letters? So B from here is the base space, which is on the other side also. So what is this thing? This is called the classifying space. Classifying space. for M bundles. And these square brackets denote homotopy classes of maps. Okay, I will say a few words about this classifying space in a second, but let me maybe before I do that, maybe let me tell you how this correspondence works. So how does this correspondence work? So you start with your map from B to this magical space B diff of M. And it turns out that the space B diff of M comes equipped with something else, namely with a universal bundle. So this is called the universal bundle. And so this is, if I have this map F down here, then this correspondence works by sending this map F to the pullback bundle F star EM. And so this classification result down here, let me maybe box this. This classification result down here tells you that every bundle, every fiber bundle over the base B with fiber M is somehow contained in this universal bundle. So this is some kind of intuition what this space B diff M looks like. So this is like a space which knows of all the bundles and which kind of has all the bundles in there. So it's huge. So if you have never seen this before, you may just take this as a theorem that there is this space and that it has the property that every bundle is given by that it has this universal bundle, and every bundle over some space is given as somehow lying in this universal bundle. Okay. So this is this classifying story. And now we have, well, I said I kind of defined the notion now. So like the first thing is now you want to start studying those things. And well, as an algebraic topologist, you are used to look for invariants of these things. So let's look for these. Oh, and maybe this is a good point for me to make a remark. So as of now, I have 3 different notions on the board. So I said something about manifold bundles, said something about fiber bundles, and I said something about M bundles. And the reason why I have these 3 notions is that probably if I just continue talking, I will mix them up. They will all mean the same thing. So whenever I say one of these 3 words, this will be, the same thing. Just as a warning that I hope my concentration lasts long enough to use just one wording, but it will probably happen. Okay, so what's a place to look for those invariants? Well, one place is the cohomology ring H star of the classifying space of this B diff of M. So if I have a class in here, let's call it K. And if I have my map F from this side, then I have an induced map F star to the cohomology H star of B. And I can apply this map to K. And this is what I define to be K of my bundle E. Okay, so well, now I defined this thing. So what's the cool thing about that? Well, first, this K of E is natural with respect to pullbacks. So in order to say what this means, maybe let's write down, let's say we have a map alpha from B prime to B. And let's say we have our classifying map for a bundle E over B. Again, we have this commutative square. We have our bundle E here, which is just, well, E just the pullback of the universal thing. And then let's also assume I want to pull back this bundle to B prime. And so, well, let's look at this thing. Alpha star E prime, alpha star E is just alpha star F star EM, which is just F after alpha star EM. And well, now I want to look at, I can look at the characteristic classes for these. So let's see what happens if I take this class K of E and pull it back with this induced map alpha star. So this alpha star is now not like a pullback of bundles, but the pullback map on cohomology. So this is just, by definition, alpha star of F star K, which is equal to F after alpha star of K. And now this map, this F after alpha, is a classifying map for my pullback bundle. Because, well, it's a map from B prime to B diff. And it has a property that, well, if I pull back the universal bundle along this map, this is just my bundle I start with. And so by the definition I just gave you of what the characteristic class of the bundle is, this is K of the pullback bundle. And so what I end up with is the following naturality. I want to pull back this characteristic class Kappa of E, K of E. This is just K of alpha star E, which if you have seen maybe characteristic classes of vector bundles, this is one way, this is like the other way to define them. So you say, well, a characteristic class is a cohomology class over my base space, which satisfies this naturality condition. And yeah, this is what's kind of built into this definition if you just think of characteristic classes as cohomology classes of this big classifying space. And something else which comes out of this is that this association from E to K of E is actually an isomorphism invariant. And I mean, if you just take this homotopy classes of maps thing as a definition for bundles, then this is absolutely immediate because, well, cohomology is homotopy invariant. So if you have two homotopic maps, that would induce the same map on cohomology. So you get the same characteristic classes for homotopic maps. And yeah, if you have isomorphic bundles, you get homotopic maps. So that's something nice to have. And yeah, so this is why this H star of B diff of M is called the ring of characteristic classes. Okay, so that's some set of invariants, and actually that's kind of nice because, well, that's most of the words in the title already appeared in the talk. So I have talked about characteristic class of manifold bundles, and I have kind of this collection of all of them. So let's now get to spheres, and in order to do so, let's look at the ring of not characteristic classes, but only of rational characteristic classes. So that means let's look at Hn, nth cohomology of B diff, of M with rational coefficients. And now the advantage of working with field coefficients is that you have your universal coefficient theorem telling you that this is isomorphic to the homomorphisms from the nth homology of B diff of M into the rationals. And now we can compare homology to, well, something related to spheres, namely to homotopy groups by means of the Hurewicz homomorphism. So we can apply the Hurewicz homomorphism. This goes from the homotopy groups of the space to the homology. Because I'm considering homomorphisms, then I can pull back along this Hurewicz homomorphism, and I get to homomorphisms from high n of B diff of M into the rationals. And I want to go even one step further into the homomorphisms high n of H out of M mod diff of M into the rationals. Okay, so what is this space here? Well, this is another classifying space, as one could guess, and it's the following. So this is the classifying space for homotopy trivial M bundles. So again, this classifies M bundles, but I have a homotopy equivalence of the total space with the product. And this is a homotopy equivalence over B. Okay, and I mean, yeah. Obviously, if I have a bundle which has some extra datum, it is a bundle. So I have a map from H out mod diff to B diff by just forgetting that it's homotopy trivial. So I again get a pullback map in the other direction. So this is what this map up here is. And now I want to make the final, not the final, but the following definition. So let's take a class, a characteristic class. I like to say universal characteristic class, and we say it is called spherical. For M, if K is non-trivial in this homomorphisms from the homotopy group. So it survives if I want to consider bundles over spheres. And I say it's H spherical for M by kind of the same definition, namely if it's non-trivial in 2. And I mean, you probably could guess what 2 is. and it is correct. So we now have this definition of what a spherical characteristic class is. Well, let me make two remarks. First, a class K is spherical if it is spherical, then there exists an M bundle over the sphere E to S N with K of E non-trivial, and it is H spherical if I additionally know that additionally to this there being a bundle, it's H spherical if also this bundle E is homotopy trivial. So if E is homotopy equivalent to M times Sn. And again, this is a homotopy equivalence over Sn. So asking if a characteristic class is spherical kind of asks the question if it is realized by a bundle over the sphere. Okay, so this is the first remark I wanted to make, and well, the second is kind of obvious, and it is K, it's H spherical. K being H spherical implies K being spherical. Well, which is obvious because if it has survived down here, it has to survive before. Okay, but well, let's just, the other way is not clear. So I mean, something could be non-trivial in here and be in the kernel of this map. So this is something that's possible. So let's now get to the questions I want to answer today. The first question is which characteristic classes are spherical or H spherical? And the second is related to this, the reverse direction up here, namely, does the reverse hold? So does K spherical imply that K is H spherical? Okay, so this is what I want to talk about for today. But before I can do this, I need to go back one step, because I ask a very specific question because I want to know which characteristic classes have a certain property without saying anything about what kind of characteristic classes there are. So first, in order to talk about this, I need to talk about what kind of characteristic classes are there. Okay, and this gets me to the topic of Kappa classes, and sometimes they are called Morita, Miller, Mumford classes. So how does this work? Well, instead of starting with the cohomology of B diff, which is hard to understand and probably very large, let's start with something we do understand, namely with the cohomology ring of the classifying space for the orthogonal group. So this contains all characteristic classes of vector bundles. So in this particular case, if you look at rational cohomology, all you get are Triagin classes. And so yeah, this is the ring of Triagin classes, and these are concentrated in degrees divisible by 4. And so if you have one of these classes, let's say we have P, we can evaluate this on any vector bundle. And well, a particular vector bundle is the vertical tangent bundle of the universal bundle. So, well, first of all, let me first write down where this bundle actually lives. This is a bundle over the total space of this big universal M bundle I talked about before. And the idea is the following. So if this is what your fiber bundle looks like, so if you have your base B, then you have all those fibers. And then at a point in this total space, well, you know you are in one fiber. The fiber is a manifold, so you can just look at the tangent direction of this fiber. So you can look at the tangent space of this fiber, so either this TEX, EEX here, or TE prime, EX prime here. And then the collection of all of these is the vertical tangent bundle. So this is vertical tangent bundle T of M. And now for the map, which is a little harder to define or harder to explain, this is denoted by lower Schrig. And this goes kind of in the wrong way, because I mean, cohomology is contravariant, and this map goes in the direction of the map pi, of this projection map pi. And this goes to the cohomology of B diff of M. And maybe write this out, P of T B E M. And well, maybe instead of explaining what this map is, let me give you the name. This is the sometimes called Gysin map or fiber integration. So if you are interested, you can look it up, and you will probably get a better explanation than I can give you in like 1 minute. And so this class back here is defined as the Kappa class associated to the characteristic class P for vector bundles I started with. Okay. So, well, this is one way to define characteristic classes for manifold bundles. And sometimes these Kappa classes are also called tautological classes because, well, they are kind of very easy to define because they come from these characteristic classes of vector bundles. And yeah, now, well, we have answered these, or I have answered this first question, what kind of characteristic classes are there? So I think now it's time for a theorem. So let D be smaller than 4M, smaller equal minimum for D minus 1 over 3, comma 3D minus 5 over 2. And let's assume that M simply connected. So it's connected and the first homotopy group, the fundamental group vanishes. Okay, and let's pick a monomial, p equal pi1 to pin in the cohomology H for M of BOD with rational coefficients. So this should be a monomial in rational Pontryagin classes. And now let's answer the question when the associated Kappa class is spherical or H spherical. So first, if this is actually a non-trivial product, so if P is not just the single top Pontryagin class, then the associated class Kappa P is H spherical. If for M, if and only if the product pi1 of Tm to pil of Tm to pin Tm with this middle thing left out. So this now is some monomial in Pontryagin classes of my manifold M I start with. And the statement is that the class Kappa P is H spherical if and only if this class is non-zero for some L. Okay, so we have one case left, which is the case of PM, P being PM. So let's look at Kappa PM, and this is H spherical if and only if it is spherical. So again, we have for a particular manifold M hanging around here, if it is H spherical, and this happens if and only if there exists an integer I such that Pontryagin class, the ith Pontryagin class Pi of Tm is non-trivial. So this kind of answers question 1 in a, well, kind of complete way. So it answers it for monomials completely. And so about question 2, well, part 2 of this theorem is a partial answer to that, because it tells you this one top class is spherical, satisfies this implication. But this is not always the case. So for P equal to P1 to the M, Kappa P is spherical, but not H spherical. For the manifold Cpn times Cp to m minus 2n. And then there is some condition on the indices hanging around. Okay, and I should also mention that this last part is joint work with Jens Reinhold. Okay, so, well, that means I now have answered these questions. So maybe let me give a little one more remark what this final thing actually means. It means that, well, if we call this M for a second, this final part means that there exists an M bundle E over S to N. So this is just to make up for, to make all the indices fit. S over 2n with P1 of M of the total space is non-trivial. And no such bundle satisfies the condition that it is homotopy trivial. So none of these bundles is homotopy equivalent to M times S to N. Okay. So now this is main result. So maybe before I start talking a little bit about the proof, let me present two applications. One is fibering cobordism classes over spheres. So let me recall what a cobordism is, or what it means to be bordened. So if I have two manifolds, M and M prime are called bordened, and I'm talking about orientedly bordened here. So they're called bordened if there exists a manifold W of one dimension higher, such that the boundary of W, del W, is given by M disjoint union minus M prime. Picture you should have in mind is the following. So I have my two manifolds, M and M prime here, and I say they are bordened, they satisfy this relation if I can connect them by a big manifold, one dimension higher. And this curious minus sign comes from the fact that this cobordism has a direction. So one time my orientation is showing into the cobordism, and on the other side it should point out of the cobordism. So this is the reason for the minus sign. And okay, so this is what it means to be coordinate. And now the corollary I get out of this theorem from before, actually out of part, yeah. And then this requires actually part 3. It is for any k smaller equal 8 and any oriented manifold n with dimension of n being at least 4 times this k, there exists a natural number g, the g-fold connected sum of n with itself is important to some fiber bundle E2 SK. Okay. And so yeah, again, let me mention this is joined with Jens Reinhold. And we also have a, well, a theoretical mathematician would say kind of unsatisfactory answer. We have an answer for the base sphere being smaller or equal than 12, with the additional assumption that dimension of n is smaller than some large number. So yeah, this is computer aided, which feels a little unsatisfying, but yeah, we weren't, that this is the best we could do. So this is first application I wanted to mention, and the second one is a little more, has a little more of a geometric flavor, because it is about the A hat class. So what is the A hat class? Well, the easiest way to say it is some polynomial in Pontryagin classes and it is of total degree for M. And one fun fact about it is, which is also the reason why it has received a lot of attention, is that if my underlying manifold, if M satisfies the condition that it admits a spin structure and it admits a metric of positive scalar curvature, then this A hat class of M vanishes. Okay. And now about the promised corollary. One, if M, my manifold M is as in part 2 of the theorem before. So if it is like this over here, so it has some non-vanishing Pontryagin class, rational Pontryagin class, then kappa A hat M is spherical. And yeah, now I told you before, this has some application to the geometry. So this implies there exists a CP2n minus 1 bundle E to SK, which is homotopy equivalent to the trivial bundle. So if you look at it very coarsely, this looks actually like the trivial bundle. And this bundle admits no metric of positive scalar curvature. Which is a little counterintuitive because, well, you have a fiber which is positively curved. It's yeah, the strongest form of positive curvature you have. The base also is, because it's a sphere, and the total space is so negatively curved in a sense it doesn't even admit the weakest positive curvature condition. And the same result is true for HPN and P2. Okay. So maybe can you remind me, I have 1 hour or 50 minutes?
You have an hour.
Okay, thanks. So the remaining roughly 15 minutes, let me talk a little bit about the proof, i.e. let me sketch the proof. And well, first let me start with the observation that this kappa P class is H spherical or spherical. If and only if there exists a bundle, an M bundle, E over the sphere, some base dimension, which you can solve. So this K is determined by your characteristic class P and the dimension of M. So if there exists such a bundle, such that if I take the characteristic class P of the tangent bundle of the total space, and then I evaluate it against the fundamental class of the total space, that this is non-zero. Okay. So I want to understand these kind of bundles. And well, of course, the place for the where I need to look for this is the homotopy group of this classifying space of homotopy trivial M bundles. So this is the classifying space which showed up in the definition of H spherical. And it turns out that this homotopy group is isomorphic to the relative structure set from surgery theory. So before I explain what this structure set is, let me remark that this only holds if where M minus D is roughly smaller than D over 3. So the precise estimate is the one which shows up here. But this is like good enough. So if you have this, then this homotopy group of this classifying space is is isomorphic the structure set. So what is this structure set? This is the set of tuples X, which is a manifold with boundary X being S for M minus D minus 1. So the same times M, so the same boundary as the manifold I plug in here. Plus the second thing I have is a homotopy equivalence from X, to D for M minus D times M, which is trivial on the boundary. So if restricted to the boundary of X, this should just be the identity. So this is the definition of this relative structure set. And it is well, I need to quotient something out, namely, I need to quotient out diffeomorphisms. So if I have two diffeomorphic manifolds x and x prime, such that the diffeomorphism commutes with this map F, then I identify these two in a structure set. And the intuition behind this is that, well, this contains the set of all manifold structures on a given homotopy type.
Is F a homotopy equivalence?
Yes, I didn't say this. Yeah, thanks. Yes. So yeah, the point is you think of you think of plugging in something, and then you look for all manifolds which are homotopy equivalent to the something. And yeah, this is the structure set. And in this case, it's like a relative structure set because I want it to be the identity on the boundary, or like fixed on the boundary. So what's this good for? The point now is that the structure set is accessible through surgery theory, through the long exact sequence, the surgery exact sequence. And what does this look like? So I have my structure set of d for m minus d times m. Then from the left, I have a map from an L group. So this is the L group in dimension 4m plus 1 of the integers, which is trivial. So I have a long exact sequence starting at 0, or a exact sequence starting at 0. And the next group is the group of normal invariants. D for m minus d times m. And the final thing is again an L group, L for m of the integers, which is isomorphic to Z. And this final map is roughly the signature of of something. And turns out that the set of normal invariants is rationally isomorphic to the real K theory of S for m minus d smash m plus. Well, I didn't tell you what normal invariants are, but basically this looks similar to the structure sets. We have again a manifold, but instead of a homotopy equivalence, you have a degree 1 map, and you have a substitute for like the normal bundle of your, like the stable normal bundle of your manifold X. And you just forget every extra datum and just consider this stable vector bundle. And yeah, it turns out that rationally, this is enough to describe this. And then I can go on from K theory via the Pontryagin character. Which is like a little cousin of the Chern character to the for ith cohomology, reduced cohomology of sk, or s for m minus d, smash m plus, again with rational coefficients. And this again, just like the Chern corrector is an isomorphism, this also is an isomorphism rationally. And it turns out that, well, if I have a stable vector bundle in my K group up here, this Chern corrector allows me to actually get a grip on the Pontryagin classes of this vector bundle Xi. So the ith Pontryagin class of Xi is given by some constant, so some sign. Well, I've learned to not care too much about signs in my life. So this is a constant depending only on I. And times the ith component of this Chern, this Pontryagin character. And since this is a rational isomorphism, I get the following statement for all. So yeah, for all classes xi in the cohomology in H for I minus for m minus d of m, there exists a vector bundle, a stable vector bundle, such that pi, the ith Pontryagin class of Xi, is given by plus minus this constant times some positive integer, or some non-negative, some non-zero integer, times the fundamental class of my sphere times this class xi. And the slogan behind this, which is the last thing I want to tell, is that one can describe Pontryagin classes of Xi. Okay, and so the point now is one has a lot of freedom in choosing these. So I can just choose classes in the cohomology of M, and this again should be rational cohomology. And I know there exists a normal invariant that has these satisfied, that has Pontryagin classes which I can choose. And then I have to make sure that the signature vanishes. So then I get an element over here in this structure set, which means I get a bundle such that this certain Pontryagin class I wanted to have does not vanish. So, and I didn't want to say describe, prescribe Pontryagin classes, which hopefully makes more sense. And yeah, the main work now lies in solving this combinatorial problem that you want to have Pontryagin classes with certain properties. And maybe one final thing I should say is a disclaimer that the underlying idea was pioneered in a preprint in an article by Sandai Coopers, Manuel Kranich, and Oscar Randall Williams, who proved, go back, a special case of this first part of the A hat corollary with basically the same ideas, the same underlying ideas. So they proved that the class A hat 3 is spherical for the quaternionic projective plane. And their idea goes along the same lines, which is the basis for the proof of my main results. And yeah, this is the last thing I would like to say. So thank you for your attention.
Thank you very much. Thanks, Georg. I have a few questions myself, but let me see. Are there any questions from the audience? All right, I asked you. One basic question, you said that in one of the examples that you had the product of the projective spaces, you said that if the
hang on, this one down here.
yes, that one. You said that if the if this power of the Pontryagin classes are not zero, then it's not homotopically trivial.
Yes.
Why is that?
So basically you can read it off this first part. So you want to have the property that P1 out to the m-1 is non-trivial for your manifold. And the point is the total degree of this class is for m-4 then. So and if n is at least 3, then your base space has dimension at least 6. So there's simply not enough cohomology for this class P1 to the m-1 to survive. So this is the reason why it can't be H spherical. And for the other part, well, you have to construct the bundle. Does this answer your question?
Yes. There's one other, maybe two other questions out of curiosity. So the reason that you care about spherical classes, is that because you care about the homotypic groups of, say, B diff or the odd mod diff, and as a way of detecting non-trivial classes in homotypic groups, or there are more geometric reasons behind it that you care about spherical classes?
So yeah, the main reason why I was interested in this is actually this ahead class thing. Because if you have bundles like this, so let me maybe open a new slide and start writing down stuff. So if you have a bundle, you have some fiber M, then a total space, and then a sphere, such that E admits no positive scalar curvature. So what do I want? I want M admit positive scalar curvature and E not. Well, then you can say, okay, this is kind of hard to motivate, because the actual motivation comes from studying spaces of Riemannian metrics with of positive scalar curvature. So if it's okay, this will take like a 3, 4, 5 minute detour. So basically you have an action of your diffeomorphism group on this space of all Riemannian metrics. So this is space of Riemannian metrics. And I want to also have this additional condition that there's some geometric condition that the scalar curvature is positive. And then you can ask when is this action actually trivial? And whenever you have such a bundle, this tells you that, well, this bundle is classified by an element here, which is isomorphic to by k-1 of diff of M. So it corresponds to a k-1 family of diffeomorphisms. And if you have a bundle like this, for a bundle like the above one, I know that this corresponding family acts non-trivially. So if I now look at this family Ft, which belongs to this bundle, ft t in sk minus 1. And I look what it does with a sum Riemannian metric. And I know that this family, which is like given by an orbit of this action here, then this family is non-trivial in by k minus 1 of this R plus M space. So this was like the original motivation. And yeah. So once I had this, I saw.
So you're saying that if, so what was the hypothesis? If this class in the homotopy group,
so basically, if this bundle satisfies this property that while this the fiber is admits positive scalar curvature, so this admits this geometric condition, whereas the total space does not. Then I know the family classifying this E acts non-trivially. And so there's a way to find non-trivial elements in this this homotopy group down here. And yeah, I mean the basic, the easiest kind of abstraction to positive scalar curvature is the A hat genus, which I mentioned before, that if you have a spin manifold, then the A hat genus is an obstruction to this geometric condition of positive scalar curvature. Then yeah, so then I have a bundle satisfying this, and yeah, so I get a result like this here. So basically, this now amounts to constructing bundles with non-trivial A hat class or A hat genus, and this was the main motivation. And yeah.
See, now that you said this, in higher dimensions, is it possible to fiber a negatively curved manifold over sphere?
I'm not sure. Because I mean the tangent bundle of E will always decompose in the tangent bundle of the sphere and the tangent bundle of the vertical tangent bundle. So you will always have these positively curved directions of this base sphere hanging around. So my guess would be no. But I'm not sure. I mean, this sounds like a hard question. So maybe what I'm saying is very wrong.
But you see, in dimension 3, somehow roughly all the hyperbolic manifolds up to cover, they fiber over circle.
Yes.
And this is somehow surprising.
Yeah, but I mean the circle is like one dimension too small to see curvatures, right? So I don't know. I would need to think about that.
All right.
Yeah, sorry. I think I can't answer this question.
No, that was good. Any other question? So I clap on behalf of everyone. Thank you.
I think
I'm gonna stop the